Okay, well, we need to get started today. So, believe it or not, it's the last week before spring break, which is fun to think about. Okay, so we're going to continue on today with chapters 5, and we're going to start chapter 6. And the course does seem to always move fast the further we go along. So, even though it's still a few weeks away, but with the spring break, there's not many classes before then. So, I want to send you the first notification about the next exam review. So I won't dish you guys this time. I will have an exam review. And that's going to be on Friday, March 23rd at 1 p.m. And it's going to be in this classroom. Okay? So that will be recorded and posted to YouTube, and sometime about a week before that, I'll have a sheet, like a review sheet, posted on Blackboard that has all the questions we'll go over. But that's when it's going to be, just if you want to start marking your calendars and getting ready for that, and having, since we didn't do one the first time especially. The other thing that I want to remind you about is the homework assignments. In case there's any confusion about how that works over spring break, so there's currently Chapter 5 Homework 2 just opened up yesterday, and it's not going to be due until after spring break. So there's just one homework assignment for the next 2 weeks. If you finish it this week, and then you can peace out during spring break. But if you need more time to work on it or want to, you can have that open during the spring break week as well. So what we're going to start today is a quick review of stoichiometry, which we started last time. We didn't do too many examples, so let's just start with one here. Yeah, it works a lot better if only one person's talking. Thank you. Iron metal. So in this problem, we're going to talk about a reaction between iron and water. So iron reacts with water to form magnetite, Fe3O4, and then hydrogen gas is formed as well in this reaction. So we want to know how many grams of water are required to react completely with 25.0 grams. Yes? I think this is the finish of the notes from last class. So I reproduced these first couple. I might skip one because of time, but this one I think was in the previous one as well. So depending on how you're following along, you may have seen that this exact same problem was duplicated in the last notes. We just didn't get to it. Thank you for bringing that up. All right, so we have this type of problem here. We want to know how much water is required to react with 25 grams of iron. And whenever we're doing a stoichiometry problem, the very first thing we always have to do is write a balanced chemical equation. We can't do anything without that. So we have to use the words in the problem to help us do this. So we have iron metal reacting with water. So any metal by itself is just the single monoatomic species. So in this case, Fe. We react that with water. I think we all know what water is, H2O. And then the two products of this are going to be Fe3O4 and hydrogen gas, H2. So as we said, most non-metal gases are diatomic, so H2 is one of those, and we'll learn more about that later in the semester. All right, so those are the reactants and products, and now it's just a matter of putting the coefficients in like we did last time, and learn how to do that. So as I said, I like to set the most complicated species to a coefficient of 1. The one that has the most atoms in it is usually how I decide that. So Fe3O4, two elements, 7 atoms total. Let's set that to 1 and then balance everything else relative to that. So if we go to the reactant side, iron only appears once, Fe only appears once, so we can balance that with a coefficient of 3. And then we have oxygen only appearing once on each side. So on the product side, we set this to 1, so there's 4 oxygens. And so we want to have 4 oxygens. On the reactant side, we put a 4 in front of H2O. And then finally, we need to figure out what to do with hydrogen. So by adding this coefficient of 4 here, we now have 8 total hydrogens. So we want to have 8 on the product side. We also need a 4 there. So that's the way to balance it with lowest whole number coefficients. When you're doing stoichiometry problems, if you balance it with fractional coefficients, or if you balance it with not the lowest whole number ratio of coefficients, but other ones, as long as they work, they're fine. They're gonna get the same answer in the problem. So it doesn't have to be the lowest whole number coefficients, but that's typically how I'll do it. So this one works, but there's other combinations. If you had 6 irons plus 8 waters goes to 2 Fe3O4 and 8 hydrogens. In other words, if you doubled all these coefficients, the problem would still work. So we can check ourselves to make sure that it's balanced. We went through all this, so it should match up, but just to make sure after we're all said and done, we compare the number of each element on the reactants and product side. Okay, so on the reactant side, we have 3 irons. Each one has 1 atom in it, so it's a total of 3 iron atoms. And then on the product side, we have 1 Fe3O4. Each has 3 irons. So that matches up. So iron is balanced, hydrogen. On the reactant side, we have 4 waters, each with 2 hydrogens, so a total of 8. And then on the product side, we have 4 H2s, each also with 2 hydrogens, still a total of 8. And then for oxygen, this is a pretty simple one because each element only appears once on each side. We have 4 waters, each with 1 oxygen. And then we have 1 Fe3O4, each with 4 oxygens, total of 4 for that. So everything balances out on both sides. We should, if we have time, we can always check that. So this is our balanced chemical equation, and now we have to go through and figure out what the problem is asking us to do. So we're going to have this balanced chemical equation, which I'll rewrite here so we have convenient access to it. Alright, so we're going to do the proper conversions that we need to do to figure out what this is asking, which is how many grams of water are required to react completely with 25 grams of iron. So when we're setting up problems like this, as I've always done, I start with what we're looking for, which is the grams of water. Start with what we're given, which is the mass of iron that's going to react with that. And so we're going to do a bunch of conversions to figure out how many grams of water are required to react with this mass of iron. And what we have to remember is that the coefficients in the chemical equation that we just balanced deal with molar amounts, moles of iron, moles of water. So whenever you're doing a stoichiometry problem, one of the first things you should always think about doing is converting into moles. So that's, in the vast majority of stoichiometry problems, going to be your first step. If you're not given moles, you have to convert into it. So we want to go from grams of iron into moles of iron. And as we've now seen many times now, if you have an element, you use the atomic mass to convert between grams and moles. If you have a compound, it would be the molar mass, which is the related quantity. So this is just a simple element, so we find the molar mass of iron on the periodic table. There's 1 mole for every 55.85 grams. And I can't stress enough the importance of writing out your units, because now we know that the grams cancel out and that we're actually dividing by the atomic mass. If you try to memorize, do I divide by the atomic mass or multiply the atomic mass, you're likely to mess it up. But if you write out the units, it becomes very obvious what you have to do, because we want that gram unit to cancel out and go into moles. And then from here, once we have moles of one substance, we can convert into moles of any other substance in the chemical equation by using the stoichiometric coefficients, the numbers that are out front. So if we want to go from moles of iron into moles of water, which is what we're looking for grams of water, but this is the next step, we again put moles of iron in the bottom so that it cancels out here, and we just use the coefficients in the balanced equation. So there's a 4 in front of water, so a 4 goes up there. There's a 3 in front of iron, so a 3 goes down there. Moles of iron cancel, now we're in moles of water. And then finally, the last step, we want to find grams of water, so it's always good to keep looking back at the problem and make sure you know what it's asking. We gave you the molar mass of water, which is 18.02, so that's what we're going to use to go back into grams. This time we're going from moles to grams, so we want moles to cancel out in the bottom. And then so we're going to put the molar mass in the numerator of this unit conversion factor, 18.02 grams of water per 1 mole. Alright, so this is a very common, very typical mass-to-mass stoichiometry problem. Grams into moles, moles of one substance into moles of another, and then moles back into grams, making sure you use the correct atomic or molar masses each time. And so with this string of calculations, we should get a number that's something like 10.8 grams of water. Alright? So if we're using 25 grams of iron, 10.8 grams of water is the exact right amount of water we need to do this reaction completely to form Fe3O4 and hydrogen as the 2 products. Alright, so any questions on that fairly typical one yet? So if you had like a fractional coefficient, you mean like a 15 halves? Yeah, so sometimes that comes up. You don't have to necessarily convert it to whole numbers. It's just that, because these are all mole ratios here, so this is 4/3. So if you would balance this a different way with fractional coefficients, it it would be two different numbers here, but the ratio would still be 4/3.
So let's say, for instance, like in terms of balance, like you have 3 moles of iron, and then say for instance that let's say for the water, you had 5 moles of water. So you're going to have 5 oxygens on the reactant side. And then how would you balance it on the reagent side? On the reagent side, you're going to have 5 moles of water. How would you balance it on the product side?
Well, it'd be like 5/4, I guess. Then if you wanted to, yeah, you would take it and multiply it by the denominator of that to get rid of all the fractions. So if you had a 5/, I don't think we'll usually have anything beyond half integer coefficients. It's probably rare to have anything beyond that, but I suppose you could in some problems. But yeah, you'd multiply whatever if you have fractional coefficients and you want to get rid of them, you multiply every single coefficient by the denominator of that fraction. Whatever you do to one coefficient, you have to do to all of them to keep it balanced. Now that said, for a stoichiometry problem, you don't even have to do that because these ratios will be the same whether if you have a fraction in one of your ratios, you'll still get the same answer at the end of the day, because as long as it's correctly balanced, any combination of coefficients that balances it properly will lead to the right answer. But yeah, but for balancing the equation, most of the time if we ask you to balance an equation, we will specify that you should use whole number coefficients. So that's something that you'll have to know how to do on its own. For problems like this, however you choose to balance the reaction, as long as it's correctly balanced, it'll work out fine for you. All right, so that's the end of simple stoichiometry. We're going to continue on with some things that are very closely related to and still use a lot of these same concepts, which is the idea of limiting reagent or limiting reactant. They have the sort of same, they're synonymous, they're used interchangeably really, reagent and reactant. So to help understand this concept, I think some people think this is really lame, some students like it, so we'll see which category you're in after I go through it. But let's use a culinary analogy to figure out the concept of limiting reactant or limiting reagent. So when we did stoichiometry problems up until now, we were calculating in that last one, for example, the exact amount of water we needed to react with 25 grams of iron. But let's say we're in a situation where we're mixing two reactants together and they're not in the exact ratio. How do we figure out then how much product can form or how much of one reactant is going to be left over at the end of the reaction? And that's what the concept of limiting reactant is. And to help you get this, let's look at a culinary analogy. So I haven't made this in a long time, but I do make guacamole once in a while. And I'm not going to tell you all the ingredients because I don't want to give away my secret, but I use 6 avocados, 3 tomatoes, and 2 limes, plus some other things, to make about 2 pounds of guacamole. So let's say I wanted to have a huge party at my house, which I often don't usually do, but if I did, and I go to Fiesta and I clean out the shelves and come home with 28 avocados, 17 tomatoes, and 14 limes. How many pounds of guacamole can I make? So again, the recipe calls for a 6:3:2 ratio. I came home with just some random collection, some random assortment of ingredients. So I want to figure out how much I can make from that. And so we can almost think of any recipe as a chemical equation where we have our reactants are the ingredients. So if we combine those 3 ingredients in those ratios, we get 2 pounds of our guacamole. This is not a normal chemical equation because we have different units for everything, but it works the same way. It's ratios of ingredients giving us a certain amount of product. So then what we do is we can figure out, well, if I had 28 avocados, and assuming I had the correct amount of everything else, what's the maximum amount of guacamole that I can make? So for each of the ingredients, we're going to figure out if I had this much of one of these ingredients, how much of the final culinary masterpiece could I make? So if we had 28 avocados, from the recipe we know that if we want to make 2 pounds, that requires us to use 6 avocados. So if we had 28 avocados and enough of everything else, we could make 9.3 pounds, which is a lot, but that's how much we can make from 28 avocados. Let's say we had 17 tomatoes. That's the other thing we have here, or one of the other things we have. And if we assume we had enough of the other ingredients to make, in the right ratios to make everything else, we could get from 17 tomatoes, there's 2 pounds formed for every 3 tomatoes that we're using. So that's what the recipe tells us. And so with this, we'd be able to get somewhere around 11 pounds. And then if we had 14 limes, we know that we can make 2 pounds of guacamole if we had 3 limes, I think it is. No, 2 limes, sorry. So with 14 limes, we could make up to 14 pounds of guacamole. And so we get 3 different numbers here, and this tells us then that for this amount of ingredients that we have, the avocados limit how much of the guacamole we can make. All right, because we can only make 9.3 pounds with this much avocados. We don't have enough avocado to use this many tomatoes or this many limes. So this is an example where the avocados limit the amount that we can make. And that's the exact same concept that applies in limiting reactants or limiting reagents. If you mix together two or more reactants in some ratio, one of them is going to limit how much of the product you can form. And that's the concept of limiting reactant as well. So we're going to see then how that works in chemistry situations. So the first thing we have to do when we're doing a problem that involves limiting reactants is determine which one is the limiting reactant. Because once you know what the limiting reactant is, once you know the species that's going to limit how much of each product you can form, all of your stoichiometric calculations have to start with that. Because that's going to determine then what's the actual amount of product that can be formed. So there's 2 ways to go about finding the limiting reactant. The way your book does it works fine, but I think it's not as clear as the way that I do it, but that's just personal preference. So I'm going to teach you both, introduce both of them, although I have a preferred method that I'll get to in a second that I'll pretty much always use. But the way that your book does it, I call it the long way. It's not really that much longer than my way, but maybe a little bit. So what we're going to do is we're going to determine the moles of each reactant. So when we do a limiting reactant problem, we're going to tell you that we have a certain amount of each reactant present in the reaction. And those might not be the exact right ratios of those that you need to react completely. So we're going to tell you that there's an amount of each reactant, and we're going to use those to determine moles of each one. So let's say we have just 2 reactants as a simple starting point. I'll call them A and B. Alright, so the first thing we'll do in a limiting reaction problem is determine the moles, and the way that I do it is the same. Now here's how your book does it. Your book just says, randomly pick one of the reactants and determine how many moles of the other reactant are required to react with that. So now that we know how to do stoichiometry, if we know the moles of A, for example, we can figure out how many moles of B are required to react with that many moles of A. So, or you could do it in the opposite direction. How many moles of A are required to react with that many moles of B? So you determine how many moles of B, the second reactant, and that just comes from the mole ratios in the balanced chemical equation, as we just did. So you determine how many moles of B are required to react with that much A. Alright, so you're going to get an amount of B that is required to react with how much A you have, and then that number is either going to be bigger or smaller than the amount of B that you actually have. Okay? And so if the amount you calculate is less than the actual amount of B present, and this is where this method gets confusing in my opinion. You have to remember sort of the distinctions here and really internalize this. So you calculate an amount that is less than the actual amount of B present. So that means we have more B than we actually need. This is another way of saying this. That would make A the limiting reactant. And then the opposite scenario applies if the amount you calculate is greater than the actual amount of B that you have. Alright, but you have to be able to keep these 2 scenarios straight from each other, and kind of rationalize, when I do this calculation, what does the result tell me? Is it telling me that A or B is limiting reactant, or or neither in some cases. So I think this way works, but it's not my preferred method for doing it, but I just wanted to introduce it in case you're following along with the book and that's what you choose to do. There's nothing wrong with it. The way that I like to do it, which it has one drawback that I'll point out when we get to it, but it's a little bit faster in my opinion, and it very quickly allows you to identify what the limiting reactant is. Because in these types of problems, as I said, you don't want to start doing any calculations. You don't want to start calculating the amount of product that can form or the amount of one other reactant that's going to participate. You don't want to start doing any of those stoichiometry calculations unless or until you know what the limiting reactant is, because that's where the starting point for those types of calculations is always going to be. So this method that I use allows us to very quickly determine which one of those is limiting reactant, and then we go from there. So what we're going to do is determine a new parameter that I refer to as stoichiometric ratio. So back, many years ago when I was your age, I was taking this class. This is how I was taught to do it, and it's just sort of stuck with me over the however many years it's been since I took Chemistry 1. I guess it's been about 14 years or something like that. So anyway, we're going to determine the stoichiometric ratio for each reactant. So this method still requires us to determine moles of each reactant because stoichiometry revolves around moles. And the stoichiometric ratio, which I'll abbreviate as R, is you take the moles of that reactant and you divide it by its reaction coefficient, so the coefficient from the balanced chemical equation. All right, and so you're already going to have the balanced equation in front of you because you're not going to start the problem without that, as we talked about. And then once you calculate moles of reactant, you divide the two to get what's called a stoichiometric ratio. And then the reactant with the smallest stoichiometric ratio, the smallest R, is going to be the limiting reactant. I left a word out. Sorry. The reactant with the smallest R is the limiting reactant, which I'll also abbreviate as LR. Okay? So once you find this stoichiometric coefficient, stoichiometric ratio, you find which one has the smallest stoichiometric ratio. That immediately tells you what the limiting reactant is. Now the downside of this approach, and what sometimes trips students up, is once you've used the stoichiometric ratio to determine what the limiting reactant is, at that point it becomes an entirely useless quantity, so you don't want to use it ever again. Alright, so you use it to identify the limiting reactant, but you cannot then start doing calculations with it because in most cases it's not a particularly meaningful quantity. So the warning here is that once you know what the limiting reactant is, any subsequent calculation you do any subsequent stoichiometric calculations are going to start with the moles of the limiting reactant. Okay? So you don't use the stoichiometric ratio that we calculated and then start your calculations from there. In some lucky cases that would work, but it's generally not going to work. You want to start with the moles of limiting reactants. You have to go back and use this quantity up here whenever you're starting any calculation. Okay? So just be a little bit careful with that. Don't abuse the stoichiometric ratio. Don't use it for anything but finding which one of those is the limiting reactant. Right? Okay, so let's go through then and answer then a question that often comes up, and this is for many students the confusing part about limiting reactant problems. We just learned how to do stoichiometry problems, so then how do I know if I have to determine the limiting reactant? So how do I know I can't just start doing the stoichiometry problem like I always did before in the first part of this chapter and what we just did at the beginning of today? So there's really two scenarios that you're going to encounter in problems that you do. So if we give you the amounts of two or more reactants, so we tell you that you have this many grams of one reactant, this many grams of another, or any other amount, whether it be moles or volume of solution, as we'll talk about in Chapter 6. If we give you amounts of two or more than two reactants, you must first determine which one of those is the limiting reactant. Alright, so this requires you to read the problem carefully and see, are we telling you exact amounts of two of the reactants or more than two of the reactants or not? And if we are, you have to figure out which one of those is the limiting reactant. So don't just grab one of those numbers and start running with it. You have to then take the steps necessary to figure out which of those is going to limit the amount of product that's formed. And then the other thing that we should keep in mind is the other situation that could sometimes happen. So in many of these problems, like the ones we did in the beginning of Chapter 5, we would only give you the amount of one reactant. So if we're given an amount for only one reactant, you assume that that is a limiting reactant, and you just start the problem normally. Alright, so in a lot of problems we'll say, this many grams of one substance reacted with excess of another substance, or we don't tell you anything about how much of the other substance we have. If you only know the amount of one substance that's a reactant, then you can assume that that's the limiting reactant. You don't know anything else about the other ones. And then alternatively, if we're starting the stoichiometry problem or setting it up in the way that we give you an amount of product, so we say, how much of this reactant is necessary to form this many grams of product. Well, if we're giving you the amount of product, you don't know anything about the reactants, then limiting reactant doesn't even really matter because you're just using the amount of product to start your calculation. So there's a few different ways we can set up these types of problems, but the key point on this slide is that if we give you the amounts of two or more reactants, you have to determine which one is the limiting reactant before starting the problem. Alright, so let's go through an example of this. Alright, so let's say we do the fluorination of ammonia, so NH3 plus F2 to give N2F4 and HF. So we already wrote the balanced chemical equation, so you don't have to worry about that part of it this time. And we want to know how many grams of N2F4, which is one of our products, and we gave you the molar mass, can be obtained from the reaction of 5 grams of ammonia with 15 grams of F2. Alright, so when we're doing limiting reaction problems, remember, we know that this is a situation where we need to do that because we told you we had 5 grams of ammonia, which is one of our reactants, and 15 grams of F2, which is our second reactant. We don't know which of those is going to be the limiting reactant at the outset. The other thing to keep in mind is that the mass amounts don't tell us which one the limiting reactant is, so just because we have a smaller mass of ammonia does not mean it's a limiting reactant, because stoichiometry, remember, revolves around moles. So we can't use mass amounts to tell us that, so we have to go through the steps that I introduced to figure out which of these reactants is limiting. Okay, so the first step in that is going to be to determine the moles of limiting of each reactant, and then we'll figure out from there which one's limiting. And this is not a total waste of time because we're going to use these molar amounts of one of the reactants to start whatever calculation we're doing. So it's still, we still need this number anyway, or could use this number anyway. So we're going to find the moles of each reactant by using the molar masses. So the moles of NH3, we have 5 grams of that. And in this calculation that we're going to become so familiar with, we'll get sick of it, we're going to use the molar mass 17.0. I guess they only gave you one decimal place. So 1 mole of NH3 has a mass of 17.0 grams, and that gives us 0.294 moles of NH3. Alright, so that's moles of one reactant. We find the moles of the second reactant, which is F2. We have 15 grams of F2. And the molar mass of F2 is 38. So 38 grams per mole. Grams cancel, and that gives us moles of F2. Alright, and as I said at the beginning, it's not enough for us to know which of the reactants has the lower mass. We can't use that to tell us what the limiting reactant is. It's also not enough to know which of these has the fewer number of moles. That by itself also does not tell us the limiting reactant. As I said, the step we have to then take is determine its stoichiometric ratio, which I abbreviate as R. Alright? So now that we have the moles of each reactant, we're going to use those to determine stoichiometric ratios. For each reactant. So for NH3, we take the moles of NH3, which is 0.294. These are technically unitless quantities because we're dividing a mole amount by a mole amount, so I'll just leave units out for now. And so we divide this 0.294 moles of NH3 by the coefficient for NH3 in the balance equation, which is a 2. Okay, there's a 2 in front of NH3, so that's what we divide by. So it's 0.147. And then we do the same thing for F2. We found that there were 0.395 moles of F2. And then the coefficient for F2 in the balance equation is a 5. Alright, so there's a 5 in front of F2, so we divide by that. And we get a stoichiometric ratio for F2 of 0.0790. And our goal is to identify which of these two numbers is smaller. So clearly this one is smaller, which means that F2 is the limiting reactant. Alright, so even though we have a larger mass of F2, even though we have more moles of F2, when we do this last step, it comes out that F2 is our limiting reactant. Alright, so we've identified that F2 is the limiting reactant, and then from here is where we can start the calculation as we normally would. But as I said, we have to be careful not to use this number again. So this number, now that we've determined that F2 is the limiting reactant, that number is completely useless. So what we can do then is start the calculation. So the third step in this is to do whatever calculation is required to get the answer. But we have to start with whatever our limiting reactant is, in this case F2. Alright, so the amount of NH3 no longer matters at all, at least for this step, because NH3 is the excess reactant. Whatever is not the limiting reactant is going to be what's called the excess reactant. So we have to start everything with the limiting reactant. So we're looking here for grams of N2F4. And we're going to use moles of limiting reactant as our starting points. Remember, we don't use the stoichiometric ratio that we found. We just use the number of moles. So there are 0.395 moles of F2. Or alternatively, we could go back to the beginning and start with the grams of F2 and just redo that conversion. But we already did it once, so we don't need to do that step again. So we've already determined that there are 0.395 moles of F2. We have moles of our one substance. We're going to convert into moles of product by using the coefficients, the mole ratios from the balanced chemical equation. So we want moles of F2 to cancel. We want to find out how many moles of N2F4 can be generated from that. So there's a coefficient of 1 in front of N2F4, or there's no coefficient, so it's assumed to be 1. And then for F2, as we already saw, there's a coefficient of 5. So that gives us moles of product that we form. And then finally, to get grams of product, as we've already seen, we use, again, the molar mass. So 1 mole of N2F4 has a mass of 104 grams, as we're told. So that converts into our grams of product, which comes out to 8.22 grams, assuming I did my math right. If any of these numbers ever look wrong, just stop me, because I'm not taking the time to calculate them as I do them. I calculate them ahead of time, and it's possible I messed up. But I think that's the right number. You get 8.22 grams of N2F4, so that's the maximum amount of product you can form, given that F2 is our limiting reactant. Right? Any questions on that? Alright, now another question we can now start to ask is how many grams of excess reactant remain after the reaction? So whatever reactant is not the limiting reactant, or if there's more than one, there could be more than one in this, if there's 3 or more reactants, whatever is not the limiting reactant is going to be considered an excess reactant, and what that means is there's going to be some of that left over at the end of the reaction. So NH3 is our excess reactant, so we're not going to use all of the NH2 that we put in, and there's going to be some amount that's left over. In this last step here, we're going to figure out how much that actually is. Alright, so if F2 is limiting reactant, that means NH3 is in excess. And what we're going to do is we're going to calculate, if we know that there's, again, 0.395 moles of limiting reactant F2, how much of our NH3 is going to react with that? So we're going to look for the mass of NH3 that's consumed in the reaction first. So we have 0.395 moles of limiting reactant. Remember, every calculation that we're going to do is going to start with that. And from the balanced chemical equation, we have coefficients of 2 in front of NH3, 5 in front of F2. So that means for every 5 moles of F2, 2 moles of NH3 react. So moles of F2 in the denominator, moles of NH3 up top. And then we have 2 moles of NH3 reacting for every 5 moles of F2. Again, that comes directly from the coefficients 2 and 5 in the balanced chemical equation. All right, so that tells us how many moles of NH3 are reacting, and then the last step will be to figure out the mass amount, because we're looking for how many grams are left over. So we'll convert this mole amount into a mass. We're told earlier that the molar mass of NH3 is 17.0, so 17.0 grams per mole. It allows us to calculate the mass of NH3. So the number we get here is 2.69 grams, and that represents the amount of NH3 that is consumed, or that is going to be reacted with the F2 to form the N2F4. So that's how much NH3 reacts, and then we want to find how much is left over. We have to consider the amount we started with. So the mass of NH3 that's in excess is the amount we started with. So at the very beginning we told you that we're putting in 5 grams of NH3. So this is our starting amount. We subtract out the amount that is consumed in the reaction, which we just determined was 2.69 grams. And that means that 2.31 grams of NH3 are left over at the end of the reaction. Okay? So this is what it means to be an excess reactant. Of the 5 grams we put in, only 2.69 reacted and 2.31 were left over at the end. Okay, so that's another little thing we could ask you to do in some of these problems, is determine the amount of excess reactant that's still available at the end of the reaction. All right, any questions on those ones? All right, since this is an important topic, we'll just finish with one more long drawn-out example. You can try it on your own if you want, before or after, but let's just go through it. I think I'm skipping part 1 here. All right, so we have the following balanced reaction. I think I left the slide out by accident, but that's okay. We can do this anyway. We have N2O plus sodium plus NH3 going to sodium azide, NaN3. This is the explosive that's used in airbags, and then NaOH and N2. So a pretty complicated reaction, but we gave it to you. It's already balanced, so nothing there. We want to know how many grams. Yeah, I left the slide out. Now we can't do this, can we? Well, we can, because I have the notes in front of me. So we're going to combine 5.25 grams of N2O. I can't believe I messed it up. All right, we have 5.25 grams of N2O, which is 44.01 grams per mole is the molar mass. 4.05 grams of sodium. And 2.57 grams of NH3. So in this case, I'm giving you all of the reactants and how much we're using. All right, so it's a little bit of a step up from the last one, because now I'm giving you the amounts for 3 reactants. So same set of steps, but just a little bit more extended now to figure out what the limiting reactant is. Okay? So this is the end. Okay, so the last thing we're going to do is we have to figure out which of these are the limiting reactants. So we're going to find moles of each reactant. So we have N2O, sodium, and NH3. So we're going to find the moles of each reactant first. We have 5.25 grams of N2O. And the molar mass is 44. So we get 0.119 moles of N2O. And then from there we're going to find the stoichiometric ratio, which is this amount divided by the coefficient. So moles is 0.119. The coefficient in the chemical equation is 3 for N2O. So that gives us a stoichiometric coefficient, which 0.040. Okay? So we took the moles divided by the coefficient, and we're going to do that for the other two reactants now. So it's a little bit repetitive, a little bit tedious at times, but we have to do it to figure out which one's the limiting reactant. So for sodium, the moles of sodium is going to be 4.05 grams of sodium. And it's an atomic species, so we're just going to use the atomic mass, which is given anyway. Let's convert grams of sodium into moles. And so with those numbers we get 0.176. And then the ratio for sodium is going to be that number, 0.176, divided by its coefficient. We go back up to the balanced equation, coefficient of 4 for sodium. So we divide that number by 4 to get 0.044. So a little bit bigger than the first one, so that one definitely can't be a limiting reactant. And then the last one that we have is NH3. We have 2.57 grams of NH3. Molar mass of NH3 is 17. So same set of calculations, just 3 times for the 3 different reactants. We have 0.151 moles. And its ratio is going to be then that number divided by its coefficient, which is just a 1. So it's the same number. Okay, so the smallest of these 3 stoichiometric ratios is going to tell us what the limiting reactant is. That's clearly going to be N2O. So we've identified N2O as our limiting reactant. And then what the question asks us is how many grams of NaN3 are theoretically obtained, or the most amount that can be obtained. So once we determine limiting reactant, which is the long part of this problem, we're just going to then calculate the mass of sodium azide, NaN3, that can form. So exactly the same as the last problem. We have our moles of limiting reactant, which is 0.119. So our limiting reactant is N2O, so we're starting with the molar amount of that. So 0.119 moles. We use the coefficients in the balanced chemical equation to convert moles of N2O into moles of NaN3. So there's a coefficient of 1 in front of NaN3 and a coefficient of 3 in front of N2O. And then we use the molar mass, 65.01, to convert that amount back into grams, which is what we're looking for. And that comes out to 2.58 grams. Which would match up with choice D. Okay? So same set of steps, just a little bit more complicated because we have 3 reactants instead of 2. But anytime we have amounts for 2 or more reactants, in this case they're all gram amounts, we have to go through some process to figure out which one's the limiting reactant before starting the problem. As I said, there's some variations in how you do this, so if you have the book or you have a way that you're already familiar with from a previous course, use whatever is familiar to you, but this is kind of the method I use. Alright, the last topic we're going to cover in Chapter 5 is this theoretical yield, actual yield, percent yield business. Okay, so this is more of a experimental look at how we do chemical reactions. So everything we've done up until now on pencil and paper is just calculating amounts of reactants that are involved in a chemical reaction, or calculating the amount of product that can potentially form in those situations. But what we actually have in many cases in the laboratory is that we don't get the exact amount of product that we think we can get for various reasons. So what we have are 3 terms here: theoretical yield, actual yield, percent yield. Theoretical yield is the maximum amount of product that can be formed. if all of the limiting reactant is consumed. Or in other words, this theoretical yield is the amount that you would calculate using stoichiometry. You know what the limiting reactant is, you know how much you have, you calculate how much product can form, and that is what's called your theoretical yield. It's the maximum amount of that product that you could potentially form in this reaction. Now, actual yield is the amount that is obtained experimentally. And normally, in most of the problems we do with percent yield and all these things, are going to give you this amount because you can't really calculate this amount. But this is the amount of product that is obtained experimentally. It will always be less than or equal to the theoretical yield. Right, so you can't get more product than you expect. That would violate the law of conservation of mass, among other things. So it's the amount of product that's obtained experimentally is the actual yield when you go in the lab and do the reaction. And there's a few reasons why, in many cases the actual yield is not exactly equal to the theoretical yield, why it's less in most cases. So one is, what's called experimental losses when you're doing, I don't know if in Chem 1 lab, I don't know if you probably do some chemical reactions and measure yields and things, but when you do a reaction in a laboratory setting, some amount of your product could stick to the reaction flask, some amount of it could be dropped if you're ham-handed, or some amount of it could evaporate if it's a volatile product. Whatever the case is, you sometimes just lose some of your product, and that's one of the reasons then why the amount that you get at the end of the reaction may not be exactly equal to what you calculated it would be. So that's a very common thing that occurs. It's impossible to completely avoid that, although of course you can minimize it if you have good lab technique. Another possibility is what's called side reactions. So side reactions are, there's two possibilities for side reactions. One type of side reaction is where two or more of the reactants in your reaction do something else as well. So in other words, they can react in two different ways to form two different products. So that would be a side reaction that generates a different product than the one that you actually want. And so if you're using some of your reactants to do something else, you can't form the maximum amount of product that you calculate. Or sometimes the product forms and then it reacts with something else that's in the reactant. So either two products react with each other to do something else, or your product reacts with the reactant to do something else. So in other words, these side reactions are just unwanted reactions that sometimes happen at the same time as whatever reaction you're studying. And that can limit your yield as well. And then another case which you'll talk a lot about in Chemistry 2, if and when you take that course, is that the reaction just doesn't go to completion. This is often a situation that we refer to as equilibrium in many cases, where basically you don't get 100% formation of the products. You're going to have a situation at the end of the reaction which is some of your reactants still haven't reacted, some of the products have formed, and there's a mixture of reactants and products, and you'll learn all about that in Chem 2, so we don't need to know the details of that. But those are three reasons why your actual yield may not equal your experiment, or your theoretical yield, or in most cases does not. Now once you have both of these quantities, you can calculate a percent yield, which is just the ratio of the two divided by 100. So it's actual divided by the theoretical yield. And because it's a percent, we have to multiply it by 100. And if you do the problems correctly, or if you're doing your lab work correctly, whatever the situation, this should always be less than or equal to 100, because your actual yield is always less than or equal to your theoretical yield. Okay? So that's just one other thing we can calculate now once we get, it's just a little small extension. And as I said, usually in these types of problems, we're going to give you the actual yield, and then you'll calculate percent yield. But we could do it the other way. If we told you what the percent yield was, and we gave you enough information to find the theoretical yield, you could solve for what the actual yield would be. So that could be your unknown, but there's no way to calculate that using stoichiometry. So the actual yield you can't calculate using stoichiometric calculations. That's either going to be given to you, or you have to use this equation and rearrange it to calculate actual yield, if that's what we ask you to do. Most of the time we'll just give that to you. And here's an example where we do. So we have this ugly looking grayish black powder. It's called tungsten hexachloride, WCl6, and it can be prepared by, or I guess the more appropriate name is tungsten 6 chloride. It can be prepared by direct reaction of elemental tungsten and chlorine gas. And so if we go into the lab, we combine 5 grams of tungsten, 6.75 grams of chlorine gas, and then at the end of the reaction we obtain 5.92 grams of WCl6. What is the percent yield for this reaction? Okay, so this is going to be a few steps to get this. We should recognize right away that this amount here is our actual yield. So if in a problem we're telling you how much of a product we got, that would be what your actual yield is. And then if we're actually to calculate the percent yield, you would need to find the theoretical yield to go from there. So finding the theoretical yield is just a stoichiometry problem example we've done 2 of already. So we have amounts of both of our reactants, tungsten and chlorine. So we need to go through and write a balanced reaction, figure out which one's the limiting reactant, and then calculate the amount of product. So those same sequence of steps that we've already done twice already. So we need a balanced reaction, tungsten plus Cl2 to make WCl6. This one's pretty easy to balance. We just need a coefficient of 3 in front of Cl2. That gives us 6 chlorines on both sides, one tungsten on both sides. So that's the chemical equation, and then as I said, we have to go through and figure out which one's the limiting reactant. So the first step is to find the moles of each, and then their stoichiometric ratios. So starting to beat a dead horse now, we have 5 grams of tungsten as well as how much we put in, and we convert that into moles. I neglected to give you the molar masses, but the tungsten is an element, so we find its mass from the periodic table is 183.84. It's one of our heavier transition metal elements. So we cancel out grams, and that gives us 0.272 moles. And then the ratio, R, is going to be that number divided by its coefficient. As I balance the reaction up here, there's a coefficient of 1 in front of tungsten. There's no coefficient written. And so that's going to be the number that we get for tungsten. We do the same thing for Cl2. So we're told we're using 6.75 grams of chlorine gas. Its molar mass is just 2 times the atomic mass of chlorine, or 70.9. Alright, so I didn't give you that number here, but you should know how to find it now. We stop there to get moles first. So I got 0.0952. And then the stoichiometric ratio is going to be that number divided by the coefficient of 3, which I got 0.0317. So those are the 2 stoichiometric ratios. The one that's smaller is identified as limiting reactant. So here you go. Tungsten has a smaller ratio, so it's going to be our limiting reactant. So that's the first step, is to identify that. Then the second step is going to be to calculate the theoretical yield. And what I mean by that is just calculating the amount of product that can form in this reaction now that we know what the limiting reactant is. So again, the chemical equation is this. And our theoretical yield is just the mass of WCl6 that can potentially form once we know what the limiting reactant is. So our limiting reactant was tungsten, as we said, and we saw on the previous slide there's 0.0272 moles. I'm going to calculate the amount of product that forms. That's going to be 1-to-1 mole ratio. So 1 mole of WCl6 forms for every 1 mole of W. tungsten. That's because they both have coefficients of 1. And then we're going to use here's the molar mass. I didn't give those to you before, they're here. We're going to use the molar mass that's given to us for WCl6, 396.54. Convert that into grams. Now I suppose one thing to maybe point out in case it wasn't obvious, when we're calculating percent yields, we can divide either the masses of theoretical yields and actual yields that we get, actual yield divided by theoretical yield in terms of the gram amounts, or we could do it in terms of moles. It would be the same ratio, obviously, but since we're given the mass of product as our actual yield, let's just do that in terms of everything in terms of grams, which is more conventional anyway. So we're going to calculate the grams of WCl6 that can potentially form, which comes out to 10.8. And this, again, is our theoretical yield. Okay? So that's what that number represents. That's the maximum amount of tungsten 6 chloride that we can form in this reaction. And then finally, the last step, once we have that number, is to calculate percent yield. Alright, so there's the equation again that we introduced. Actual yield over theoretical yield times 100. So our actual yield, as we said, is given to us. We're obtaining 5.92 grams of WCl6. The theoretical yield that we just calculated was 10.8. That's the maximum amount we can form with 5 grams of tungsten as our limiting reactant. And then we multiply by 100 to get it into a percent. And this comes out to 54.8%. Okay? So we got 54.8% of the maximum amount of product we could have gotten in this reaction. Alright, any last questions on stoichiometry, percent yields, limiting reactants? Because I think this is the end of chapter 5. It is. So we're going to move on to chapter 6 here in a second if everyone's all squared away on that for now. Alright, so you'll have again another homework assignment on chapter 5 this week, so you see a lot of those themes in there. It's actually not due till the end of spring break, as I said. And so you'll get a lot of practice on this on the homework assignment this week, and now we're all caught up for that. So all that's left now is to move into chapter 6, last chapter before the second exam. And so we're just going to get this started a little bit today with some definitions and some things, some conceptual things before talking about other details related to this chapter. So chapter 6 deals with our reactions that happen in solution. So when we have a solution, it's going to be we have to define what that is. We're going to now talk about chemical reactions that happen when the reactants are dissolved in the same solution. And some different features of those, some different types of stoichiometry calculations that we can do for those, all kinds of things related to solution chemical reactions. So first let's define what a solution is. So it's a homogeneous mixture. That was the term we used at the very beginning of this course, which means that it's 2 or more components, but we cannot distinguish the components. We can't easily tell that we have 2 things mixed together. Salt water is the classic example of a solution. It's salt dissolved in water, and you can't tell that there's two components there once it's all dissolved. So it's 2 or more substances. And because it's homogeneous, we say it has a single phase, which means you can't really tell that it's 2 things mixed together. They're mixed completely together. You can't distinguish the components anymore. And at least in the context of this chapter especially, and really in chemistry overall, it usually involves a liquid. So most solutions that we talk about are liquid solutions, where one of the components, the major component, is a liquid. You can have solutions of 2 gases. Technically, the air we breathe is a solution of 2, more than 2 gases, really, or many gases together. You can have solutions. You can have what are called solid solutions, which another term for that is alloys, which we might touch on a little bit at the end of the course. But for this chapter, we're going to be talking about primarily liquid solutions, solutions where the major component is a liquid. So some examples of this that I've already kind of touched on already. Salt water is a very common solution. Most beverages are solutions, if you can't really tell this, but a bunch of things mixed together. As we said, air is a solution that's made up of gases instead of liquids. Gasoline is a solution. It has more than one thing in it, but looks like a single liquid phase. So those are all examples. They're physical mixtures of things that are all blended together in a way that you can't tell that there's more than one component. Now, the two components in a solution we often refer to as solute and solvent, and this is especially true when we're dealing with liquid solutions. So the solute is usually the minor component. So if it is two liquids mixed together, the one that you have less of will be designated as the solute. And in most solutions, you have way less solute than solvent, the other component being the solvent. So it's the minor component of a solution, and it's whatever it is that you're dissolving into the solution. So in salt water, the salt is the solute. It's what you're dissolving into the liquid. Okay? And then the solvent is the other thing, so it's the major component. And it's the substance that does the dissolving. In the context of Chapter 6, it's going to be a liquid. And Chapter 6 is specifically about what are called aqueous solutions, which means that liquid is usually water for our purposes. And so that's what that term means. Aqueous means dissolved in water. Alright, so Chapter 6 is all about aqueous solutions, or mostly about aqueous solutions, I should say. So let's talk about why water is able to dissolve so many things and sort of what happens when something dissolves in water. So first let's review polarity, because that's an important point for water being able to dissolve a lot of things. Because, as we'll see, what happens is that you have this unequal charge distribution in water, and that's because oxygen is more electronegative than hydrogen. So this is a review of a lot of Chapter 3 and Chapter 4 concepts. So you have these polar bonds, where you have a delta plus on hydrogen, delta minus on oxygen. It has a bent shape such that those two bond polarities are not able to cancel out. And you have, in a water molecule then, negative and positive poles. They're not full negative and full positive charges, but there are regions in the water molecule where you have a partial negative charge and then partial positive charges. So you have this unequal distribution of charges. That's what it means to be polar. And so that's kind of just a quick review of why water is polar, which is important for its ability to dissolve different substances. And so what we're going to look at here then are a couple of videos of this. We're going to look at a molecular level picture of what happens when ionic and covalent compounds dissolve in water. And so let me minimize this and go to the video. So that's this video here. I have the link in the, I hope it still works. I haven't checked it in a while. So here's what we have. As we're going to learn later on in the course, you can't really see my pointer on this page very well. It's there, very small. As we're going to learn later on in this course, when you have an ionic compound like sodium chloride, it's going to be a regular array of positive and negative ions. So the way that those ions arrange themselves, they just sort of alternate in all three directions, and you have these big blocks of alternating positive and negative ions. So let's see what happens when we put some of this in water. Come on, please play for me. Oh no. It's loading. Maybe not working. Well, I think the other video will work, so I won't be over too, hopefully. I don't know why we're having trouble with this today. Oh, limited connectivity. Too many of you are using Wi-Fi. All right, well, we might have to... Yeah, the wireless has been flaky in here today. I don't know if it's always like this, because I don't use it a lot. Or it could be my tablet's being flaky, one of those two. Oh no. Well, we might have technical difficulties that stop us from watching these today. Well, I have the links in the notes, so I encourage you to look at them on your own because I can't seem to get connected right now. But let's just summarize what happens when we dissolve compounds in water. The videos will help to visualize this. So the key point is that when you dissolve an ionic compound in water, as the graphic showed before the video flaked out, you had these positive and negative charges all arranged in the solid ionic compound. And then what happens is that water molecules come in and they individually remove those ions and separate them into the solution. So you have negative and positively charged ions. Water has a negatively and positively charged or partially charged poles because of its dipole. And so the negative dipole in water, the oxygen, is going to grab onto the positive charges and pull them out. And then the positive part of the water dipole, the hydrogen section, is going to grab onto the negative ions and pull them out. So basically when you dissolve an ionic compound in a solution, you separate it into its individual ions. Okay? So that's the key for ionic compounds. The ions separate in solution, so you no longer have the positive and negative ions associated with each other. What you have instead is individual positive and negative ions that are separated and surrounded by the water molecules. Now, if we dissolve a covalent compound in water, so polar covalent compounds will also dissolve in water, things like alcohols, for example, other things that have polarity associated with them can dissolve as well. And when you dissolve a covalent compound, you typically don't have any breaking of the bonds. All right, so the video that I had that, again, doesn't work, let's go back to it, see if I can get it to work. Or at least, don't close. All right, now it thinks I'm connected, but the video is still not starting, so... Well, what this video would show if it worked, and I guess I should have checked it before class to make sure that it still works, because I came to class unprepared, and now you guys all know that. So, if that one ever does work, I'll probably have to find an alternative if it doesn't. What you would see is when you dissolve a covalent compound in water, the molecules don't break apart. Those are strong covalent bonds, so you're not going to just totally rip the molecule apart. You're just going to have the water molecules surrounding that polar molecule and sort of bringing it into a cluster of water, and you're going to have these interactions that we'll talk about later in the course in more detail, but you don't really break the molecule apart for a covalent compound. So that's the key difference here. And then what that leads to is some different properties for the solutions when you dissolve these different things. So let's try our second one and see if I can get this to work. So this guy's pretty intense, and he wants to show us different properties of solutions. So he's excited to go. So we have all these different compounds dissolved in water. We have plain water, we have tap water, we have sodium chloride, some other ionic species. And so let's look at tap water. We see this, he's going to basically testing the ability of these solutions to conduct electricity. So we get sort of a weak, dim lighting up of the bulb. We put it in distilled water, pure water, nothing happens. Now let's look at the properties of different solutions that we have. So sodium chloride, you see you get a really bright light bulb indicating a lot of electricity is conducted. Hydrochloric acid, HCl, same thing. Sodium hydroxide, another ionic compound, lights up pretty well. So we see that when we make a solution of ionic compounds. Now let's look at sugar. This is a covalent compound. We notice that a solution of sugar does not conduct electricity, which is very exciting. And then vinegar, another covalent compound, for reasons we'll talk about a little bit later, gives us weak electrical conductivity. So it's not that all covalent compounds don't do that, but certain ones do, certain ones don't. And then ethanol is another covalent compound. We see no solution conductivity. And I think he just tasted the ethanol, which is not a good idea. And then this is an insoluble ionic compound. So it's an ionic compound, but it doesn't actually dissolve. And we see that in a compound that doesn't dissolve, you don't see the light bulb lighting up. So the compound has to actually be dissolved in water for that to happen. So that gives us then what are two different types of solutions here. So when we dissolve ionic compounds, if we dissolve those into solution, they conduct electricity. And so a solution that conducts, and we saw that also happen with some covalent compounds. We'll get to the distinction between those here a little later. But a solution that conducts electricity is called an electrolyte solution. So basically we can classify aqueous solutions into two types, electrolytes and then non-electrolytes, so not a very creative naming system, but two different possibilities, electrolytes and non-electrolytes. Come on. So one that does conduct electricity is called an electrolyte solution. And within these different types, we have strong and weak electrolytes. So an electrolyte solution could be what's called a strong electrolyte or a weak electrolyte. So a strong electrolyte would be one of those that we saw in the video that conducts electricity really well and the light bulb got really bright. A weak electrolyte would be one of the ones where we got a little bit of electrical conductivity, the light bulb was kind of dim, like the one we saw with, I think it was vinegar was the example they used. So strong electrolytes, the ones that give a lot of solution electrical conductivity, are soluble ionic compounds, are the classic examples. So we saw that in that video, all of the soluble ionic compounds they looked at, I think that they looked at two anyway, was sodium chloride and sodium hydroxide. Both of those gave strong electrical conductivity. Both of those are strong electrolyte solutions. Or the other class of compounds are called strong acids. So we introduced the nomenclature of acids, and we will talk more about the chemistry of acids in this chapter. But strong acids are these ones here. These are the ones that you should know. HCl, HBrHI, nitric acid, H2SO4, and HClO4. And so the idea with strong acids is that they behave a lot like ionic compounds. When we dissolve them in water, they separate into H plus ions and then whatever anion is associated with that. So strong acids, in terms of their electrolyte properties, are exactly like soluble ionic compounds. When they dissolve into solution, they separate out into separate ions. So you have H, those are the ones that you should know are strong acids, and they conduct electricity really well. All right, and there's of course a gray area between what are called strong and weak electrolytes. It's not an obvious cutoff point, but weak electrolytes are ones that partially break down into ions when you dissolve them. And that gives you then some ions in solution and some solution conductivity. Alright, so these are what we call weak electrolytes. They give some ions when they dissolve in solution, but they don't completely break down. And really the only category of weak electrolytes we're going to worry about in this class are weak acids, which are basically all other acids besides those that I categorize as strong above. So any other acid is called a weak acid, which means when you dissolve it in solution, it's going to release some of its H plus ions and the corresponding anion along with that, but it's not going to give you full dissociation into ions. So that's the difference between weak and strong acids, which you'll learn a lot about weak acids in Chem 2. We'll talk a bit more about strong acids in this course. And then finally, the last category is non-electrolytes, which means when you dissolve these compounds in solution, you get no electrical conductivity. And the examples of non-electrolytes that we should worry about are covalent compounds that are not acids or bases. Again, we haven't really fully defined acids and bases yet, so we'll get to that later on in chapter 6. But if it's just a regular old covalent compound, like an alcohol being the classic example, methanol, ethanol, the ones, I think ethanol is what he did in that video. These covalent compounds that are not either acids or bases, or sugar was the one he also did as an example of a covalent compound that's not an acid. Those ones, when you dissolve them in solution, they don't get any, give you any electroconductivity. So now that we know that water is polar and it's able to dissolve polar substances, you should be able to predict then if a brown bear and a white bear jumped in the water at the same time, which one would dissolve faster. Someone seems they already know the answer. It'd be the white bear because it's polar. All right, so that's. I think I'm going to skip this because this relates to what we did next time. I want to make sure I leave plenty of time for a bonus quiz. We haven't had one in a while. That graphic got messed up, but all right. So again, as quickly as you're able to, get your bonus quiz forms ready to go. There it is. Okay, so it's going to be, this one I think is numerical, but it might be helpful to have a calculator, but probably not necessary. I gave you pretty easy numbers, so in case you didn't have your calculator with you, you wouldn't suffer. And again, it's multiple choice. Pick the best answer. Only one answer, please. And don't try to trick me by putting two letters on top of each other and hoping I pick the one. No, that doesn't work. So, and work individually once we get started. Okay? So, I'll stop this now because we don't need to